in matter. Johannes got his PhD in 2012 from Northwestern University, where he worked with Bill Halperin and is an expert on superfluids, helium-3 in particular, and especially in the presence of quench disorder. And after that, so he moved to Caltech, where he was working with Jim Eisenstein on stuff he's going to tell us about today, gallium-arsenide, low-dimensional electron systems. So we're excited to hear him talk about engineering quantum matter. So we have a small token of our appreciation that we'd like to give speakers. So
this now, or?
Yeah. So that would be good.
Great, thank you. Thank you, Amy. The coffee. That's wonderful. I can't get too much coffee. So, yeah, can everybody hear me? Good? Okay, great. So yeah, like Adrian said, my name is Johannes Pollanen. I'm a postdoc in the Institute for Quantum Information and Matter at Caltech. And so I'm going to tell you a little bit about my experiences in engineering quantum matter, specifically with regard to superfluid helium-3 and electrons in 2 dimensions that are grown, that can be confined in 2 dimensions in semiconductor structures. So what do I mean when I say engineering quantum matter? Well, when I got started working in condensed matter experiment, I remember seeing images like this by researchers. This research was done by people at IBM. And what they did is they took individual iron atoms, that's these blue peaks right here, and they arranged them on a copper surface in this 2-dimensional chiral fashion. And what they've done is they trapped the electronic wave function in this chiral. And I remember thinking, okay, this is pretty amazing. We understand quantum mechanics. Quantum mechanics has been around for 100 years now, more than 100 years. And but more and more what we're doing is we're taking the individual constituents, quantum pieces, and being able to play around with them and create new systems that are interesting and behave quantum mechanically. And this is a system that's made up of atoms on this surface. And in one way or another, the theme that has run through my experiences in condensed matter physics are associated with engineering quantum matter, not individual atoms, but systems that have lots of particles, where the particles are all interacting with one another. But it turns out, even in that backdrop of all that complexity, we can still engineer those systems. We can play around with them and learn cool things. So just to give you a flavor of some of the things that you can do, while I was a grad student at Northwestern, we used these Adrian mentioned this quench disorder. We use highly porous glass structures that we filled with liquid helium-3 at low temperatures, and we were able to use those to stabilize altogether new quantum ground states. So by engineering those structures, we could change the quantum state of helium-3. But it turns out that those structures, those glass structures, are interesting in and of themselves, and you can engineer their microscopic structure and study them with optics and X-rays, which we did some amount of, and you can combine them with things like nanoparticles, metallic nanoparticles, to make composites that can be used for a variety of different applications in chemistry. Now, when I moved to Caltech, this theme continued of creating and controlling quantum systems. We built a special kind of cryostat that relies on magnetism to cool 2-dimensional electrons in gallium-arsenide down to temperatures that are only achievable in a few places around the world. With the hope that when you get to those very low temperatures, all the interactions that exist between the particles, these weak interactions, get amplified. You can see them, the particles all talk to one another, and new phases of matter can appear. And then we worked with our sample grower, and then we studied this system with a variety of techniques. We use sound waves. You can probe the electrons with sound waves, and you can do just simple resistance measurements. And those are essentially the kinds of things I'll be telling you about today. But we've also worked with our collaborators who grow these structures, because you need to interact with people who make the materials that you want to study. You know, Mother Nature provides us with helium-3, but to grow these kinds of samplage structures, you have to have good interactions with people that can make those things. And we work with our collaborators at Princeton to grow 2-dimensional electron systems in which we could produce electric fields right in the middle of the sample. Or we could create samples in which we can tune the Coulomb interactions, because there are electrons ultimately. You know, it's Coulomb interactions that are the dominant interaction. We can tune those. And then we use a variety of fabrication techniques to create other low-dimensional electronic systems. For example, one of the things that we've been interested in is studying the behavior of just graphite, thin layers of graphite, very high magnetic fields and low temperatures. But unfortunately, I don't have time to tell you about all of these things, so I'm just going to highlight 2 of these to get across this idea of engineering quantum matter. And I'll tell you about how we created a new chiral superfluid phase. I'll tell you what I mean by chiral, using these aerogels, and about how we've been working to create new device architectures for being able to tune the interactions between electrons in 2 dimensions. So the outline is semi-chronological. I'll start with this work that I did in grad school, engineering the superfluid states. And then the second part of the talk, I'll tell you about how we control in quantum matter, different kind of quantum matter, these 2-dimensional electrons, with a device that allows us to tune the density of electrons in the sample. And then I'll tell you about what I think the future holds for someone who knows about how to play with these kinds of systems. Specifically, I want to tell you about how these experiences can lead you to think about studying a new quantum system, one where you have exquisite control over the particles, where you take a layer of liquid helium and you put electrons onto the surface of that. And then coupling those, if you can manipulate that system very well, then you can couple it, you can imagine coupling it to nanoscale devices that exist under the surface, or various kinds of topological states of matter. And I'll describe what I mean by topological, at least in some hand-wavy kind of way. Let's get started. So before I tell you about how we can create new superfluid states of helium-3, I have to give everybody a crash course on superfluidity in helium-3 to begin with. So when I say superfluid, I want you to think about a liquid at low temperatures, very low temperatures, that flows without any kind of viscosity, no internal friction in the liquid. That's just one of its properties, but it's a defined one. Now you might think that that sounds a lot like another kind of phenomenon, namely superconductivity of electrons, and it is. They're very, very similar, fundamentally similar. And superconductivity is just the flow of electrical current through some material that has electrons in it, where there's no dissipation. Now, ultimately, this results in both of these systems, helium-3 and in electrons, from the fact that the constituent particles, they're fermions. And so, you might, at very low temperatures, if you have a system that's made of everything in the universe is either a boson or a fermion, right? Well, that may not be true, but for the moment, let's consider everything's a boson or a fermion. Bosons, you cool them down, they can all fall into the same wave function, and they can all become one big quantum system. Fermions don't have that possibility. But if you take 2 fermions and you stick them together somehow, there's some weak interaction that sticks them together, then that composite particle, that paired particle, those can all fall into the same quantum state. And that can create superfluidity in helium-3 and superconductivity of electrons. Now the main difference between these 2 is that when the helium-3 particles pair up, they pair up with certain quantum properties. Specifically, they pair up with total orbital angular momentum equal to 1. So they're actually orbiting each other. And they pair up with the spins a lot. Well, not quantum mechanically, but they pair up with the spins adding up to total spin momentum equals 1. And that's in contrast to the electrons, where both the orbital and the spin angular momentum are equal to 0. And feel free to just stop me at any point if there's questions. So, okay, I'm going to show you a lot of these kinds of phase diagrams. This is a point of reference for where one finds superfluidity in helium-3. So the pressure axis here on the line is just the actual hydraulic pressure that we apply to the liquid. And then the temperature scale here tells you where, how cold one has to get to find superfluidity. And this isn't a typo. We really have to get to temperatures on the order of 1 millikelvin, 1 or 2 millikelvin, to see this phase of matter. And this solid line delineates, as a function of pressure, where the superfluid lives. So everything colder than that line is where the superfluids are. And it turns out in zero magnetic field, there are 2 of them. We label them A and B. It's not a terribly creative labeling scheme, but it turns out it works pretty well. Now, the other thing that is important about the system is it's extremely clean. And this is going to be important if you want to use, say, disorder to create new kinds of quantum ground states. And it's so clean, in fact, that at low temperatures, there are no impurities in this system. At 1 millikelvin, there's just helium-3 atoms around. Even the isotopic impurity from helium-4 doesn't exist. It gets pushed out of the system. So yeah, low temperatures, think about this. Frictionless quantum fluid, ultra clean. And let me tell you about these 2 superfluid phases, the A and B phases, because it's going to be important for the rest of the talk. But all you need to take away is that the B phase is an orbitally isotropic state. What I mean by that is, if you take the wave function and rotate it in real space, or in momentum space for that matter, then it looks the same, no matter how you rotate. And that's in contrast to the A phase, which is an orbitally anisotropic state. And what I mean by that is that if you rotate the wave function, I say 90 degrees, it doesn't look like itself anymore. And you can see that from this kind of picture right here, which is not a picture of the wave function, but it's a picture of the energy needed to break up these fermion pairs. Remember, it's a paired state of fermions. And so the energy in momentum space to break those up is the difference between this outer shell that's purple and this inner green sphere. And so you can see clearly that if I take that object in momentum space and I rotate it by 90 degrees, it doesn't look the same. But in the B phase, I can rotate this thing around and it looks exactly the same. And this is ultimately a manifestation of what the underlying spatial wave function looks like. And these two phases also have different magnetic properties. If you take two spin 1/2 particles and you want to add them up quantum mechanically to give you total spin equal to 1, you can do it in 3 ways. You can add them up, down, down, or you can do this up, down, plus down combination. That's all quantum mechanics allows you to do. And in the B phase, you have all 3 of these spin states present. That's in contrast to the A phase, where you have only this up, up, and down, down combination. So okay, that's helium-3 in its pure, unadulterated form. And now we want to add some kind of disorder to that. And the reason we want to do that is because it turns out that helium-3 is supposed to be exquisitely sensitive to disorder, but it's naturally very clean. So what we wanted to do, and other people also wanted to do it, is they wanted to say, can we engineer disorder in such a way as to change the underlying ground states of this system? And it turns out yes, and the way that we do it is through a material called silica aerogel. It's a porous glass structure with about 98 or 99% porosity, so it's very empty. Here's a picture of one we grew at Northwestern. And if you zoom in on that structure, what you find is at the smallest scale, there are these little spheres. They're just silica, SiO2, and they are about 3 to 5 nanometers in diameter. And they form these strand-like features through space, where the separation between them is about 10 nanometers in length scale. Now you can compare this with the important superfluid length scale, which is how far apart are the pairs, essentially, of the helium-3 atoms. And that's on the order of tens of nanometers. So you can imagine if you've got these helium-3 atoms orbiting in this quantum state, and you jam it into this structure, it's going to bump into the strands and break apart, and all kinds of weird things are going to happen. And that's ultimately why we're interested in this. Now, here's a picture, an SEM image of one of these gels that we actually grew at Northwestern. Okay, so we've got all the ingredients we need. We have superfluid helium-3, and we have the aerogel. Now let's put them together. So when you do that, what happens is you can tell from this phase diagram again. The red lines here are just the superfluid transitions in the pure case, no aerogel. And what you can see is that when we introduce helium-3 into this aerogel, the superfluid transition temperature is suppressed. That's because essentially the aerogel the helium-3 wave function scatters off of the aerogel and it breaks them apart and moves the transition temperature lower. And the other thing you'll notice is that I've labeled everything in that new phase diagram with this B. And that's because theoretically, it was predicted that if you have aerogel that's isotropic, it looks the same in every direction to the helium-3, then it should stabilize isotropic superfluids like the B phase. And in fact, that's what was found experimentally. So that got us thinking, okay, if we somehow made the scattering of this aerogel structure anisotropic and make it look different in different directions, can we create new anisotropic states? Can we bring back the A phase or bring about new quantum ground states? It turns out the answer is yes, but we'll get to that in a second. So how do we make the aerogel anisotropic? Well, that's easy. What we do is we just take our regular old aerogel and we stretch it. Well, it turns out it's not at all that easy. These structures are highly porous. They're made of glass. If you start stretching it, it's just going to tear apart. So what we developed was a series of chemical tools. The way you make the aerogel is a chemistry process, ultimately, that we have some control over. And we can, during growth, align the strands of the aerogel along one direction as if it were stretched. And if you want to, I don't have time to tell the details, but if you're interested, you can take a look at that reference or we can talk about it after the seminar. So the technique by which we want to probe this helium-3 now in this stretched aerogel. So we've engineered the structure, we're going to jam helium-3 in, we want to measure something to tell us what's going on with the helium-3. And the technique that we're going to use is nuclear magnetic resonance. Because the helium-3 nucleus has spin, so we're going to interrogate the spin of the superfluid. So a quick reminder on NMR, if we take a spin, here the nuclear spin of helium-3 say, and we stick it in a magnetic field D, then it tends to align with that field. And if we apply transverse to that, another field, say along the x-axis here, so for all of these pictures, this blue magnetic field is always present. So if we apply this green magnetic field, it tips the spin about that field by some angle beta. Now beta is how much the spin rotates is just dictated by how strong this field is and how long we leave it on. But after we turn off this green field, then the spin is free to precess about this original blue magnetic field at some frequency omega, which is called the Larmor precession frequency. It's just given by the magnitude of this blue magnetic field and the gyromagnetic ratio of the helium-3 nucleus itself. But in our experiments, this magnetic field is actually the combined effect of two magnetic fields. The external magnetic field that we apply in the lab, that's the one we have control over, we just turn on a magnet. And then there's also the superfluid field, the magnetic field associated with the formation of the superfluid itself. The superfluid is magnetic because it has this kind of spin structure, or some kind of spin structure, and that creates a magnetic field in the liquid. And we can actually measure, by measuring this frequency, we can measure that magnetic field internal to the superfluid, and therefore learn something about it. Now we measure something else, we measure the magnetic susceptibility of the liquid. That just is how magnetic is the liquid, you know? Depending on the spin structure, there will be some amount of magnetic polarization in the liquid, and we can measure that as well. That's what we can think about this green box quantity as. And so here is a picture of the actual experimental apparatus that we use to study this, with the external magnetic field pointing up, and then these little copper cylinders here are the coils that we use to apply this green magnetic field P1, and the sample lives inside of that. Okay, so let's have a quick look at what the data, now that we have this tool for measuring the superfluid, let's take a look at what the signatures are for the different superfluid states. So what I'm showing you here plotted on the left is this magnetic susceptibility. Remember, it's just how magnetized the liquid is. And on the right, I'm showing you the frequency shift of, oh, I should mention, we've taken this magnetic susceptibility and we've divided out the normal state susceptibility. By normal state, I mean the liquid before the superfluid transition. So the transition temperature to superfluidity here is given right at 1. And so up here, the liquid is normal. And so we've divided by the normal state susceptibility, which ends up being 1. And then we can also measure this frequency shift. So the frequency shift is, remember, associated with that superfluid magnetic field. And we measure that, again, relative to what happens here in the normal state. So everything's measured relative to the normal state. And right here at this dashed line, at TC, what we see is there's a large onset of positive frequency shifts, indicating that this superfluid field is developing because the system goes into a superfluid state. But the superfluid that lives in this region, right here, has the same magnetic susceptibility, the same magnetism as the normal state. But that can only happen, it turns out, if you only have this up-up and down-down combination of the quantum spins. And so that is indicative of this A phase. Now if we go a little bit lower in temperature, what we see is another transition. Let's look only at the green data. You see a jump in the magnetic susceptibility at this black dashed line, and then a decreasing magnetic susceptibility with decreasing temperature. And what that means, what's happened then, is that the system's gone into this B phase, and it's developed this part of the spin wave function. This up-down and down-up combination doesn't contribute to the magnetization, and therefore the susceptibility drops away, it becomes less magnetic. Now we have one other tool at our disposal so that's how I'm going to identify these different phases, but we have another tool at our disposal. And that tool is, remember this angle through which I can rotate the spin with this green magnetic field? That angle beta actually allows me to rotate the spin part of the helium-3 wave function relative to the orbital part of the wave function. And it's a fingerprint of what, and it turns out that the magnetic field associated with the superfluid, and hence this frequency shift, are dependent on that angle. And now, the actual dependence is governed by a set of nonlinear equations that are really complex. It's not important for the purposes of my talk, but what I do want you to take away is that frequency shift as a function of that angle beta, has a well-defined prediction for both superfluid phases, the A phase and the B phase. And here's what it is for the B phase. And so when we take a look at our sample, what we think is the B phase in our aerogel sample, we see a set of data that match very well with this data. I don't know if I mentioned this, I meant to, but all of this that I showed you just now is for the isotropic aerogel. So this is an aerogel which we have not stretched. This is just supposed to be a point of reference. And then we can do the same thing for the A phase, and we find this is what the theoretical prediction is. And again, the data is in good agreement. So this is, you may not know why these equations come about. And frankly, the theory is I'm an experimentalist, and at some point, you lean on your theory collaborators for the theory. And but what I do want you to take away is that this and this don't look anything alike. So this tool of measuring the frequency shifts is a fingerprint of which superfluid phase we're in. Okay, so now we can have a look at what happens in this stretched aerogel. Let's put our superfluid in there and use all these tools to figure out what's going on. So what we find is that as a function of pressure, at all these different pressures, we see onsets of positive frequency shifts, indicating that we've gone into some kind of superfluid state. So now we have a superfluid. Let's figure out what superfluid it is. And let's take a look at the magnetization, this magnetic susceptibility of the superfluid. And what I'm showing you here is for this non-stretched aerogel as a point of reference again. So here's the superfluid transition temperature. In the non-stretched aerogel, we find an A phase onsets, and then there's a jump in the susceptibility in the B phase. It's just the same data I showed you before. Whereas in the stretched aerogel, for all of the pressures that we measure, we never see a jump in magnetic susceptibility. We never see a reduction in the susceptibility. And what that means is that we have this combination of spins present, looking like it's the A phase. But what we can do is we can turn to those tip angle dependent measurements of the magnetic field. Remember, there's a clear prediction for what one should expect in the A phase, and again, we find good agreement with the data. So what this tells us is we actually have, in this anisotropic aerogel, we have the A phase present. And so with that data, I can draw another one of these phase diagrams for you. This time, instead of this region being filled with the B phase as it was when we had the non-stretched aerogel, what we found is that when we stretch this aerogel, we in fact get an anisotropic phase akin to the A phase. In fact, it is the A phase. So just to drive home this point, one of the things that I think is really amazing about this, you might have thought earlier that there's this, it's funny, electrons become superconductors, helium-3 becomes a superfluid. Those things are nothing alike one another, right? But it turns out fundamentally they are at low temperatures very similar. And that there are these similarities between these two systems that on the surface of things look very different. But another example of that kind of similarity is that these kinds of chiral, I forgot to mention what chiral was. Okay, so chiral just means that it's associated with this anisotropy. So the A phase is a chiral phase. It has a handedness to it, like it's different left-handed and right-handed. But these kinds of weird anisotropic phases have recently been predicted to exist in an altogether completely different system, in graphene. So if you stack layers of single atom thick layers of carbon atoms, then you can possibly find superfluid states that are just like this, which is pretty amazing. So okay, with that I want to change gears, and now I want to talk about, I've shown you an example of how we can engineer new states of matter that simply wouldn't exist otherwise if we didn't have the tools that are our capability to introduce disorder in a controlled way in helium-3. But now I want to tell you about how you can control other states of quantum matter by other techniques. Specifically, I want to tell you about these two-dimensional electrons that I've been studying at Caltech, where we can tune the interactions between the particles. So again, let me start with some, just at a level that gets everybody on the same page. What I want you to imagine is a sheet of two-dimensional electrons in a magnetic field that's perpendicular here. Now, if we think semi-classically about this problem, those electrons just whirl around that magnetic field in these closed loops, cyclotron orbits. And the frequency of that cyclotron orbit is just proportional to the magnetic field that we apply. Now, this picture allows you to look at a lot of the physics that's interesting in this system. For example, in the interior of this sample, away from the edges, what you find is the electrons are whirling around, they're localized. And the interior of the sample is actually insulated. There's no electricity that flows, right? The electrons are just, whirling around. However, on the edge, those electrons want to whirl around that magnetic field as well, but they bump into the edge, and then they skip around, and they have to hop along this edge, and they form these highways of electrical conduction along the edges. Okay? And it turns out, if you think about those edges quantum mechanically, they end up being completely dissipationless. So there's no scattering of electrons backwards. They just all hop along in this direction. Now, this is a good opportunity for me to intercept a question that I often get asked. I'm going to show you some data in a little bit where I point to regions of measurements of the resistance. So let's imagine we make a resistance measurement of this sample. We're going to push electrical current through, and we're going to measure the voltage off the side. Just simple Ohm's law, essentially. But my voltage probes are going to get stuck out here on the edge where there's no dissipation. So when I'm going to show you data where the resistance goes to 0, and I'm going to claim that that's an insulating state. And I want you to keep this picture in mind. What I mean is that the interior of the sample, where the electrons are localized by one way or another, that's an insulating state. However, on the edge, what we're going to have is these dissipationless channels of conduction. And that's where my voltage probes are. And this type of matter, this thing here, is in fact a topological insulator. If you want to just remember an easy definition of a topological insulator, just imagine a system where the interior of the sample is insulating and the edge is conducting. That's essentially all you need. That is a system that exhibits that property is a topological. Okay, so let's take a look at this just a little bit more in a slightly more sophisticated manner. Let's think about it quantum mechanically. The same system. So let's first start with zero magnetic field. If you have two-dimensional electrons in zero magnetic field, there's a continuum of energy states that get filled up. You put electrons in their fermions, they don't all fall into the same state, and so they fill up until you run out of electrons at some value known as the Fermi energy. And that's just dictated by essentially how many electrons can you put into that two-dimensional sheet. If we turn on a magnetic field, it gets a little more interesting. What happens is this continuum of energy states splits up into a ladder of what are called Landau levels. And that is really just, each one of these energy states is just a harmonic oscillator energy state in 2 dimensions. The electrons form harmonic oscillator orbits in 2 dimensions. And in fact, the energy space in between these guys, which is indexed by this integer I, is just given by the classical cyclotron frequency. But it's just a harmonic oscillator in 2 dimensions. And you can actually get this, you can see this picture of these dissipationless edge states in the insulating interior of the sample in this picture as well. If you just consider what happens to the energy of the electrons as you profile the plane of the sample. So here's the left edge of the sample, here's the right edge of the sample, and this is what the energy does. So each one of these Landau levels is flat, and then it has to rise up at the edges. And the reason it has to rise up is because the electrons can't go leaping out of the sample. There has to be some sort of confinement for the electrons are stuck in the sample. And at some point, that rising up intercepts the Fermi energy. And right here, where this Fermi energy is, that's where there are states for the electrons to jump around. Down here, they're all locked in place because of Pauli exclusion, but right here, they can run around and jump and participate in electrical conduction. And in fact, those are where those dissipationless edges form, right there at the edge of the sample. Whereas in the middle of the sample, right here, all the states are locked into their, all the electrons are locked into these states. There's no conduction. There's no pathway for conduction. So everything that I've described up to this point can be understood in terms of single particle physics. And what I mean by that is one electron in a magnetic field. You need to consider nothing else. You don't have to have 10 electrons all talking to each other. But it turns out that when you have 10 electrons all talking to each other, or 10 to the 10 electrons all talking to each other, it gets much, much, much more interesting. Because the interactions between these particles become important, and those interactions change the quantum mechanical problem, and you get altogether new states of matter, many body states of matter for the two-dimensional electrons. And you can see the manifestation of those states if you consider even just a simple measurement of the resistance of a two-dimensional state. So just stick your voltage probes on there at the end, push current through, and then change the magnetic field. So the resistance that you measure from that shows a series of spikes and minima. Some of these spikes and minima can be associated with that Landau level energy spectrum. So when you apply the magnetic field, the continuum of electron states breaks up into these harmonic oscillator states. But a whole host of these states cannot be understood in that regard. And you have to take into account the fact that the electrons are actually interacting with one another to produce these different states. And each one of these different minima and peaks is associated with a different realization of the wave function that describes all of the electrons in the 2 dimensions. And again, this is data for the system that I study now, which is semiconducting materials made of gallium-arsenide that have a sheet of 2-dimensional electrons at low temperatures. You're probably noticing also that low temperatures are important for this, because if you're at high temperatures, all of these funny little interactions that we're interested in that lead to the multitude of these states, they all get drowned out by the noise from thermal fluctuations. But you need to get to low temperatures in order to see these very weak interactions. So one can naturally ask, if all this stuff, all these quantum states, are associated with interactions between the particles, can we control those interactions and learn something new about this system? It turns out the answer is yes to that question as well. First let me tell you about the actual system, the actual physical system that I study. And that is those colors came out nice. So it's a system of 2-dimensional electrons formed right at the interface between 2 semiconducting materials. This lower layer here is gallium arsenide, and this upper layer is aluminum gallium arsenide, so it's an alloy. And when our sample grower collaborators make these structures for us, what they do is they grow them layer by layer, atomic layer by layer at Princeton, and then they fill the top side of this interface with all these silicon atoms. And silicon, because of its electron valency, provides an extra electron to the system. At low temperatures, those electrons can fall off and land on the opposite side of that interface. And that's because the energy band for those electrons is different between aluminum gallium arsenide and gallium arsenide. And in fact, it's higher in aluminum gallium arsenide. So if you've got a free electron right here, it wants to jump over this little cliff and land right at the interface. Now, it turns out that not all of those electrons want to leave their donor atom. So what we have to do at low temperatures is we have to shine red light onto the system. And that allows us to kick off the electrons on the silicon donors. And that adds to, we want to get as many electrons into this layer as possible, essentially. And so when we shine the light, that kicks those electrons off into that interface. How do we control those interactions? Well, so now we have this 2-dimensional sheet. We want to control the interactions. One way to do that is to simply add more electrons to that interface or take them out. But you'd like to be able to do that in situ during the experiment. And so the way we devised to do that, other people have done it in different ways, but the architecture that we've developed recently is to take that original structure, which is just this bilayer of gallium arsenide and aluminum gallium arsenide with 2-dimensional electrons right here, and to grow on top of that another layer of gallium arsenide that's called N+ gallium arsenide. And the N+ is just a name. What it means is that when they grow this layer, our collaborators grow this, they load that layer up with silicon. They just dump as much silicon as they can in it. And what that leads to is a whole bunch of electrons that are free to run around in this layer. And it makes this layer conductive. So then, what we can do is we can, if we can, fabricate a way to make independent electrical contact to the 2-dimensional electrons. So we push electrical current in this way, pull it out that way, make measurements. And we can make independent contact to this top layer that's conducting this N+ gallium arsenide. Then we can apply a voltage to it. And you can see this N+ layer and the 2-dimensional electron sheet looks a whole lot like a capacitor. And so if we can apply a voltage to it, we can actually capacitively tune the density of electrons in this 2-dimensional sheet. Now, you might say, well, why don't you just put a piece of metal on top of the sample? That would work just as well, but actually it won't, because what we need to do, the metal has, aside from a lot of technical issues associated with surface chemistry and things that really monkey up the sample, we need something that's transparent. Because remember, at low temperature, we have to shine light through this thing in order to deal with the silicon donors that are near the interface. And so this device structure allows us to do that. And so here's a picture of the actual sample right here, after it's been wired up onto a sample platform. And it's ready to cool down in the cryostat, take it down to millikelvin temperatures, tens of millikelvin temperatures, and study its properties. And at this point, I want to highlight somebody who's been really integral to this project, which is a Caltech undergraduate that I've been mentoring, Her name is Sarah Branson, and after my postdoc advisor and I came up with this structural design and what to do, Sarah's actually the one that had to go into the clean room and spend hours optimizing the tedious fab steps in order to make independent electrical contact to these different layers and do all that. And she's going to be giving for those of you that are going to the March meeting in San Antonio for the American Physical Society, Sarah's going to be giving a talk where she describes all of these processes and how she characterized the sample. So I won't get into any more of the fab, but if you want to talk more about how we specifically do those steps, I'd be happy to discuss afterwards. Okay, so we've got this tool now. We've got this variable density device. What do we want to go study? And let's take a look again at these measurements of the resistance as a function of magnetic field with all these interaction-produced states. So let's go have a look at one region. We're gonna zoom in on this spot, and the states, the electronic states that form in this region and give rise to the features that I'll show you here in a second, are states that are heterogeneous in space. They form states in which the electron density is modulated in the plane of the sample, and they produce all kinds of. Well, we'll get into that in just a second. But for those of you that are experts in this, this is the filling factor equal to 9 halves quantum Hall strike phase. If that doesn't mean anything to you, don't worry. It didn't mean anything to me about 2 years ago. So if we zoom in on that region, what we find is the following. So here's a plot of that resistance, those resistance measurements against a function of magnetic field. And I'm showing you 2 traces, a red one and a blue one. And the only difference between the red one and the blue one is that in the red trace, what we're doing is we're flowing the current in plane along the 1 bar row crystallographic direction in gallium arsenide. And in the blue trace, we're flowing the current along the 110 direction. These 2 measurements are just rotated by 90 degrees relative to each other. And so let me draw your attention right here to 2.7 Tesla. What you see in the red is a giant resistance peak that goes up to about 3 kiloohms or something up here. And in the blue trace, what we see is a deep minimum to 0. So it's the resistance depends really sensitively on which direction you're flowing the current. And then over here to the side, you'll notice the resistances between the 2 traces are about the same. It's a system, it doesn't care which direction, it's rotationally invariant. And so we're going to study these 2 states, this one associated with this large resistance anisotropy, and this one over here that's totally isotropic. So it turns out that the underlying electronic configuration, the theoretical underpinning for it, is thought to be the following. Right here, where this resistance anisotropy is very large, it's thought that the leading theoretical candidate for this state is where the electronic density breaks up into these stripe-like regions, where there are these elongated regions of charge density that are all lined up in the same direction. And you can imagine that it might be easy to push current along the stripes, and it's difficult to push current perpendicular to them. And that's in fact what leads to this large resistance in one direction and 0 resistance in the other. Now, it turns out that this underlying state is not just a variation of the charge density. It's much more akin, if you look at these theoretical papers, it's much more akin to a liquid crystal. So these are like liquid crystal-like blobs of electronic density that all kind of they can rotate in any direction, but at low temperatures they all shoot off in one direction. And now this insulating state here, remember I told you I'm going to point to regions where the resistance goes to 0, and I claim that it's an insulating state. This is one of them. This insulating state that formed right here, where the interior of the sample is insulated, is thought to be an insulating state. Theoretically, it's thought to be an insulating state made up of bubbles. And each one of those bubbles contains several electrons. And at low temperatures, they're thought to form a static crystalline lattice in 2 dimensions. Or for those of you that use the term, a bigger crystal in 2 dimensions. So again, here's another point to connect to, which is that these bigger crystal bubble phases have been expected to exist in another low-dimensional electron system, but they've never been observed. They've been expected to exist in graphene. But this quality of graphene samples is not sufficiently high now, today, to be able to observe these kinds of states. One really can only find them in the highest quality 2-dimensional systems that are made in gallium arsenide. So okay, we can take those, let's focus first on what happens when we start, remember we're going to start tuning the density of the electronic carriers in the system. And we can take those measurements of the resistance that I showed you previously. We're going to focus on that large resistance anisotropy right in the middle where this electronic liquid crystal that's stripe-like forms. We can take those measurements of the resistance and we can convert them into, we can change those into measurements of, we can calculate the resistivity of the sample. So we take out the geometric effects. And then we can define this order parameter. And all this order parameter tells us is how stripe-like, how well aligned are all of those electronic crystal-like stripes. And you can see that when the resistance in the direction where it goes to 0, if that really goes to 0, then this quantity tends to 1. And when it goes to 1 or very close to 1, then that means that we have well-aligned stripes in the sample, in the plane of the sample. And so here I'm plotting that order parameter as a function of temperature. So at low temperatures, where the order parameter is large, we have all the stripes all aligned, these liquid crystal blobs aligned with one another. But at high temperatures, you heat up the sample, and thermal fluctuations lead to a rotational disordering of these blobs. And up here, the resistance becomes isotropic again. And now what we can do is we can tune the density. So we can take our sample and we can pull electrons out of it. So let's just pull electrons out. And what we find is that at low temperatures, this stripe order that forms, it decreases, comes down. And what we also find is that the temperature at which this resistance anisotropy turns on, that also moves down. It just shifts downward in temperature. Now, it turns out that what this is indicating is that as we pull electrons out of the sample, the electrons are getting further and further apart from one another. So the Coulomb interaction is becoming less and less important. And that's ultimately, this kind of structure is brought about because of the Coulomb interaction. And so as we lower the density of the sample, the electronic density, we're lowering the energy scale associated with the formation of this state. Okay, so next we're going to turn to these collective, I call them collective because they can't be under these insulating states here that forms, this bubble lattice that forms, it would not come about if you had single electron physics, if you didn't take into account the Coulomb interaction. So that's what I mean by collective. And so next we're going to turn our attention to this guy and see what happens as we play with this interaction. So let's zoom in on that region. And this time, let's first hold the density fixed and then warm up the sample. And so what we find is that as we raise the temperature, the resistance right at the position of where this state exists, the resistance goes up. And what that means is that the interior of the sample is now conducting electricity. Remember, if it's 0 right here, that means the interior of the sample is an insulator, and as we raise the temperature, it slowly begins to conduct electricity. So you might think that this is somehow associated with the melting of this two-dimensional lattice of electron bubble. But actually the story is more complex than that. And you can see that if we look at the resistance where that arrow was, right where that state lives, and we plot that on a log scale as a function of 1 over temperature, the data looks like this. It increases slowly as we increase the temperature. Now, what we don't find is a very sharp melting transition. You don't see a first order transition to a melted bubble phase. Instead, the temperature dependence follows this what's called activating behavior. Essentially, just what that means is that there's some energy scale in the problem, which I label as E sub A, that you can extract from these measurements. It means that there's some energy threshold that you need to get above before the sample starts conducting electricity. And we can, from these measurements and the way we plotted this, we can extract that energy scale by fitting this data to an Arrhenius behavior, which is what this equation is. And so for this density, the energy scale turns out to be about 273 million. Okay, so now let's do something different. Let's fix the temperature. We're not going to change the temperature, but we're going to change the density. We're going to systematically lower the density, starting at 1.83 times 10 to the 11 electrons per centimeter squared. And what you can see is this data looks a whole lot like what was happening when we turned up the temperature at fixed density. As we pull electrons out of the sample, it starts to conduct electricity in the interior. It's pretty weird, right? I mean, we're pulling electrons out, and electricity is starting to flow in the interior of the sample. And so for each one of these traces, we can do this temperature-dependent measurement. So we can extract energy scale that's associated with the onset of this electrical conduction. And I can plot them up here as a function of density. And so I'm an experimentalist, and when I see data that looks like this, what I do is I end up drawing a straight line through it. Now, I don't think you should take this straight line too seriously, or exactly where it intercepts. But what it is showing is that as we pull electrons out of the sample, it's easier and easier to get electricity to flow. And that's not terribly surprising, because you can imagine if you've got the density of electrons really high, then this state, this bubble phase that exists because of Coulomb interactions, is getting weakened slowly as we remove electrons from the sample, and it begins to conduct electricity. So, if nothing else, I hope that I convinced you with that this kind of new device structure that we've developed, where we can pull electrons out of the sample, put them in, allows us the ability to control these quantum states that exist in the two-dimensional sheet of electrons. And we're working on using this for exploring other collective electron states now as well. So these two experiences of studying superfluids and these two-dimensional electrons has got me thinking about what I'm going to be doing in the future. And one of the things that I've gotten really excited about is the ability to create and control new hybrid quantum systems. And this is really specific to the reason I got to thinking about this is because of these specific experiences that I've had. Specifically, what I want to do is I want to create a two-dimensional sheet of electrons. People have done this before, but I want to also do it and then do other things with it. Create a sheet of two-dimensional electrons and put them on the surface of liquid helium at low temperatures. And then couple the motion or the magnetism of those electrons to nanoscale devices or topological states of matter that can exist underneath. So let's have a look at this system real quick. So if we take a layer of liquid helium, right here, the blue layer, and we evaporate a family of electrons onto the top, imagine somewhere we've got a wire made out of tungsten, and I pulse a current through that, and electrons come spraying out. They hit the surface, and then they see because the helium is dielectric, they see an image charge. They see a polarization that's positive beneath them, and then they get stuck to it. So it turns out this is very much like the hydrogen atom. And actually the electronic motion above this surface, if you solve the problem quantum mechanically, is just the hydrogen atom problem. So this system has a bunch of really awesome properties, some of which include it's really clean. These electrons, the only thing they see around them are other electrons and helium. And if this is just helium-4, which is the more common of the isotopes, not the helium-3 I was telling you about earlier, if this is helium-4, then that helium-4 is non-magnetic. It's very clean. It's at low temperatures. There's no disorder in the system. There's no intrinsic magnetism. And that ultra-cleanness can be measured in a quantity that we use in studying two-dimensional systems called the mobility. Now, the mobility, all it means is if I have electrons in 2 dimensions and I put an electric field, how easy is it for those electrons to start moving around? The bigger that mobility is, the better. And in this system, the two-dimensional sheet that forms here has mobilities that are at least 10 times better at low temperatures than the best systems that can be made in gallium-arsenide. So the systems that are the standard for measuring high-quality two-dimensional systems, electrons on helium, much, much cleaner. And because there's only helium and electrons around, the magnetic spin of the electron itself is predicted to have a really long spin covariance. So if I got it whirling around by some magnetic pulse, like in those NMR experiments I was applying, except for the spin, if you get it whirling around, it will stay coherently spinning, or coherently processing, for timescales that are larger than 100 seconds. That's a prediction. No experiments have been done to confirm that. Now we can also control the density of electrons on this surface, and hence their interactions. So we can pull electrons out and move them out over about 4 orders of magnitude. Actually, it's more like 5 or 6 orders of magnitude, but give or take. And because there's only electrons and helium around, the interactions between the electrons doesn't get screened by anything else, essentially. And the interactions in the system can be very, very, very strong. And because of these properties, people have wanted to harness this system of electrons on helium to create new quantum technologies, specifically those associated with making a quantum computer. And in fact, the first predictions for using this system for quantum computing applications was made by Platzman and Dykman. But since then, so they wanted to use the actual motion of the electron, its physical motion above the liquid. But since then, there have been predictions, more recently, to to use the magnetism of the electron as a qubit. And then there are various kinds of things that you can play around with the system the way that people who study cold atoms, they create quantum simulators of other systems. So you can have a series of these electrons and you can model certain kinds of spin systems with this. So like I said, whoop, that did not go well. Error reporting. Give me 1 second. My computer just crashed. Is there any questions? Ask questions now. Is the time. No question. Okay, so I mentioned that these electronic spins have these predicted long coherence times. However, this has never been measured. As far as I know, there have been no what are called electron spin resonance measurements made on this system of these two-dimensional electrons on helium. Now, these measurements are very similar to the nuclear magnetic resonance measurements I was telling you about before, and I think that they can be done if one utilizes the extreme magnetic sensitivity of a technology that already exists called a superconducting quantum interference device, or SQUID. And so imagine an electron spin near some sort of magnetic loop, and we couple the motion of that spin in a magnetic field, its precession about some magnetic field, to the input of one of these superconducting quantum interference devices. Then we can harness the extreme sensitivity that's at the femtotesla level of these systems to try to measure this coherence for the first time. And this kind of system of using this kind of SQUID magnetometer is also useful if you want to create these quantum simulators where you have many electrons and you start getting them all interacting and measuring their magnetic properties when they do kinds of nonlinear dynamical processes over long time scales. So that's one thing that I'm really interested in trying to do. The other one is that recently in the graphene community, other people that study low-dimensional systems, you probably all heard of graphene where you take single-layer sheets of carbon atoms. People now want to take those and stack them up. Say, put down a piece of graphene, and then place on top of that an insulator, like hexagonal boron nitride. And then place on top of that another layer of graphene. Now you have this graphene insulator graphene sandwich. Now the question is can you get the electrons between those two layers to start talking to each other and seeing cool quantum stuff happening? And so lots of people are working on this right now in that system. But I want you to think about a different one of these bilayer two-dimensional electron sandwiches. Take some substrate, place a piece of graphene down, or, yeah, I'll say more about that. You could put a piece of graphene down, then coat the whole thing in liquid helium, and then spray electrons onto the surface. Now the question is can you create any kind of motion of the electrons that the graphene would see if you were sensing it? Like say, let's push a current through the electron layer on the top of the helium and measure what happens to the graphene underneath. That process is called Coulomb drag, and it's never been measured in this system. It's actually been attempted to be, Coulomb drag has been measured only in, as far as I know, 2 separate systems. And people are trying to push for it in other systems, and I think this is one where you could also see that phenomenon. Now, there's one benefit to this system as opposed to the graphene system, which is that we can tune the thickness of the liquid layer between the electrons and the graphene in situ, essentially. We can change the barrier height between these two systems. And again, we can tune the electron density and hence the interactions. And I already mentioned Coulomb drag measurements, but that's just one way to probe this system. And in fact, this lends itself to a lot of different possibilities. You can put not just graphene down, you can imagine putting some other two-dimensional electron system down there. You can now create, via the same method that people make graphene single-layer sheets, via just scotch taping graphite. You can make single atomic layers of phosphorus, molybdenum disulfide, tungsten diselenide. You can create all of these layers. People are trying to create tailor-made, engineered stacks of these different materials. Okay, so we're very close to the end. But I want to highlight one other thing, which is Oh, shoot.
I had a question about the Coulomb.
Yeah.
So how can you move the electrons?
This is great. I'm glad you asked this. So, okay, so you can do it capacitively. So if you have, let's imagine you have a layer of liquid helium right here and electrons on top. And I put 3 electrodes underneath. And I put the middle one, I ground that guy. I put it just 0 potential. Now if I oscillate an electric field, this way, it will couple to the electron here and slosh it around like this. And I can actually measure, by measuring the current that flows in an AC measurement, I can slosh the electrons around and measure their properties. That's one way that people have done a lot.
You're not going to affect the electron in the direction?
This is a great question. So you're saying, so it's, in some sense that would be like a background signal, right? Like you're saying, as soon as you start shaking these charges around, you're going to see something in the graphene layer that you're measuring. But the beautiful thing about this system is you can actually remove the electrons. You can do a background subtraction. You can essentially, you may see signals. So one way to get around it is just make the geometry so that you minimize any kind of coupling to the graphene. But another way is that you can do background subtraction by doing measurement again without the electrons present. But that's a good question. It's actually. Okay, so if we have these electrons and we're playing around with them and creating these new kinds of quantum systems, can we also use them as tools to probe other systems? And I think the answer is yes. And specifically, I want to highlight one possibility, and that's to detect a Majorana particle. Now, a Majorana is a funny kind of particle. It's a particle that is its own antiparticle. You know, every particle has an antiparticle, positron, electron. But a Majorana is a special kind of particle that's theorized to exist that is its own antiparticle. And people are working specifically in, I'll highlight one work, which is Leo Coulomb group at the Technical University of Delft, where they're trying to create systems that behave in such a way that you can get a Majorana. And the reason, their motivation is that we don't have any material in nature that has the properties needed to produce a Majorana in the lab. But it turns out there's one material that is different than all the others, and that's superfluid helium-3. So imagine we have a volume of helium-3. It turns out, theoretically, there are a series of states, particles that live very near the surfaces or the walls that hold the container of liquid, where the superfluidity dies away. And in that region where the superfluid dies away, it's thought that there is a Majorana particle. And in fact, some guys at Stanford predicted that if you can detect that Majorana in the following way. Take some electrons, here I'm showing them beneath the surface, but initially you spray them onto the surface of the helium, and then you use an electric field to drag them beneath the surface, so pull them underneath. Now, if you can measure the magnetic properties of those electrons as they're pulled underneath the surface while they sit there, then you should be able to see this Majorana particle existing. And in fact, what they predict is that, here's another picture of helium. Here's a surface of helium right here, and the Majorana particles are thought to exist in this length scale right here where the superfluidity dies away, and you want to hold the electrons at some distance inside of that region and measure their properties, their spin properties. And then that would be able to, you can use, they give a clear signature of what you should expect. But I'll bring up one other point, which is that you don't actually need the electrons for this. You could also just interrogate the nuclear magnetic resonance properties of the helium-3 atoms themselves in the liquid, and those should be affected by the existence of these Majorana states. So that's another, people have proposed ways in which that can be done. So we've kind of ended where we began, which is NMR on helium-3. But I hope you guys enjoyed the journey, and with that I'll thank my collaborators and colleagues, and also the people that paid for all this work, and I'll open the floor for discussions. So the basic idea is just making these different kinds of quantum systems, playing around with them, engineering. I really think that's the future in some sense. I mean, the future is kind of now. I'm not the only one who thinks that.
Questions?
Shoot.
I remember some work done at Brown by Maris, where he would have electrons in superfluid. Don't they form these bubbles?
Yeah, it says it in the other slide, but the bubble is big. It's like 5 nanometers in size.
And he had some data that indicated charge fractionalization, but this was highly suspect.
Yeah, I would say that is a true statement. That's the way I interpret that paper as well. I think it's possible that he sees that. it's definitely one of the possibilities of what it's seeing.
So is that bubble-like formation independent of the phase of the superfluid? If you had the D phase in helium-3, presumably the electron would also dig out
A bubble, that's right. It would do the same thing. Yeah. Essentially, I mean, there might be minor corrections because the dielectric constants of helium-3 and helium-4 are a little bit different, but it's essentially a 4 or 5 nanometer bubble that forms there. Yeah. And it's the coupling to the spin that is. Other people are using these kinds of bubbles to do other fun things with superfluid helium-3. There's a Japanese group that is using them to essentially look for a flow Hall effect. So they slosh the electrons underneath the surface. They put them there, slosh them around, and then change which superfluid state they're in. And when they enter into this anisotropic A phase, they see the electrons all shoot off toward one direction. So it's like an orbital Hall effect. It's really amazing piece of work. It was published recently in Science.
I have a couple questions. So first one is related to the middle part of the gallium-arsenide. So I was a bit puzzled about the density dependence of the conductivity. You mentioned that if one decreases the density, isn't it true that the pigment crystal becomes more stable? Because dealing with low energy, but you said the opposite.
Yeah, so this is not a, so you have to remember it's a Wigner crystal of these bubbles. It's really not a Wigner crystal of single electrons. So it's a Wigner crystal more of guiding orbits. So there's many guiding orbits in each bubble. And so that doesn't follow the same kind of density dependence.
Because usually it would be the opposite.
Exactly right. Yeah, this is it.
So I guess what you would say that it's, the long range part of the bubble interaction or something is not important. Because otherwise it would be the opposite.
That's right.
So now back to the first part. So assuming that I don't know anything about helium-3, just the words helium-3. So what is the, I mean, I know it's a Fermi, right?
Yeah.
It's neutral.
Yeah.
Right? So would it be correct to say, so it's a van der Waals, so interaction or something that...
What is the interaction that actually causes the pairing?
Yeah.
Is that what you're asking?
Well, that's question A. Yeah.
Okay, so it's if you look at the interaction parameters in Fermi liquid theory, as to what they are, the leading one that's attractive is actually the magnetic couple between the nuclear spins. And so it's thought to be that, but there is no smoking gun experiment for that. It's just that that's what theory says is the most attractive.
So this is the Anderson model.
Right.
Is it right? The theory of the spin.
That's right. Yeah.
So, okay. So then, what is the basic mechanism for the formation of the A phase, which is the most exotic, right? It occupies a very small corner, and then in your experiments you expand it in an exotic way. And I think it's fair to say that we have also just a little bit something similar. So is it? So first, what are the quantum numbers of that state? So it's like a triplet without, so it's a doublet spin doublet.
It's a spin, yeah, so it's the triplet without the up, down, down, up combination.
The triplet without the third part.
That's right.
So what has caused that to happen,
In the aerogel or in bulk helium?
Yeah, just in bulk. I mean, what?
Yeah,
is it because something funky has happened to the potential?
Yeah, so the way that I understand it is that it's close to an instability with the solid. You remember so I drew that phase diagram up at very high pressures. The superfluid goes into, it stops being a superfluid if you raise the pressure sufficiently high. It becomes a solid, and it's a magnetic solid. And right there's thought to be, if I remember what Jim Sauls told me, it's that there's an antiferromagnetic instability, and that ultimately leads to the formation of GaAs. It gets rid of that third triplet. But you can see as you cool down further, eventually the B phase wins it anyway, even at high pressures.
Right.
This all gets lumped under a thing called strong coupling, which is a phenomenological addition to a Ginsburg-Lindau model that essentially.
Yeah, I was actually just looking at Anisotropic. Sauls has a paper just from this year about the Anisotropic gel.
Yeah. So Jim is our theory collaborator on all of that work.
Right.
Yeah.
So, right. So the why would one expect that if one stretches?
This is a good question.
It's an obvious question.
So I'll give my experimentalist understanding. So when you have aerogel in general, you remember the energy gap it has some finite value in either superfluid state. As soon as you add disorder, the pairs break up. And if the aerogel is isotropic everywhere, then they break up and maybe I should pull this picture up while I'm having this discussion. Because it will.
Actually, while you're switching, it's an orbital triplet. Are both phases orbital triplets? I mean, they have orbital.
Yeah, the
A phase. Momentum, and they they have the spin structure that we mentioned. Right?
Yeah,
One of
and
them
the
is
A phase,
spin-triplet.
the A phase is characterized by the global orbital angular momentum as well.
Right.
So the A phase is orbitally, it has a direction, a preferred direction in space. So here, so the A phase, it has this handedness, this px plus ipy symmetry. And that corresponds to there being an angular momentum vector that's directed along the nodes. So the way I like to think about it is this is the energy that leads to the pairing, right? And as you put the system into aerogel, this energy gets smaller. The difference between the outer shell and the inner shell gets smaller. And if the sample is completely isotropic everywhere, superfluidity starts to die away as you add more and more scattering. But it happens in the same way in all directions, essentially. But if you have a stretched gel, then you can imagine that there's some energy balance that has to strike. It can sacrifice condensation energy. As you break up the pairs, it can say, okay, we're going to kill superfluidity, we're going to kill superfluidity, we're going to push TC lower and lower. Or it might say, you know what's actually energetically favorable? Let me just pop nodes into here. Let me go into the A phase instead, if there's more scattering along one direction or another. So it has to play this, it plays this energetic balance. That's the way I think about it.
So it's not as simple as modifying in an obvious way some kind of attractive potential, right? Because
No.
the potential is very complicated.
Indeed.
It's Anders and moral spin or
That's right. That's exactly right. Though, I'll point out that you can create the A phase in other ways. You can make the A phase exist everywhere by just applying a magnetic field. You can kill off essentially this part of the triplet, and you can be left only with this up, and down curve. So if you apply a sufficiently strong magnetic field, it does the same thing. And so what we're really doing is, in some sense, applying a field in orbital space. We're doing the same thing to the orbital part of the wave function.
Yeah, so it's important that it's orbital.
Yes, the orbital anisotropy is very important. The spin is just for us coming along for the ride to be able to use as a marker for which state we have.
Yeah, in this sprayed two-dimensional electron gas.
Yeah.
What are the spin scattering mechanism, if any? I mean, diagram of Ferrer, which kills you in the 2-day in gallium-arsenide, I assume at this concentration disappears, right?
Yeah.
So
this is great.
Why 100 seconds? Why not 1,000 seconds?
Yeah. So okay, this is great. I wouldn't have been able to answer this question if I were, last month, but I can answer it now. It depends on which theorist you're asking. It really does. So the predictions for 100 seconds are from a specific proposal that take into account a bunch of different scattering mechanisms off of a bunch of different things, helium-3 impurities in the system. But I recently spoke with Mark Dykman, who's the one who proposed those, using the system for quantum computation. And he says he and a student have recently been working on this, and his prediction is the spin coherency time should be longer than the age of the known universe. This is what he told me specifically in person. And so what I take from that is, it's long, but nobody knows why. And so it will depend on whatever physical realization that you actually have. Are there wires around? Are there magnetic impurities? Is there helium-3 nuclei around? Each of these will contribute in some way, and it will depend on which. But that's actually, in some sense, that's a knob, right? No one's been able to measure the spin coherence. But if it ends up being really long, let's say it's the age of the universe, then you're in trouble, because you're never going to measure it. It's not going to happen. But if you can introduce disorder or engineer various ways that the system can decohere, then you have the possibility to measure it. Is there one question? Is that sufficient to answer your question?
Yeah, sure. But I have one more, but if anyone else is.
Right.
Yeah, so, I mean, in 2 days in gallium-arsenide, you can, of course, do optical measurements to look at speed, right? Now, I know your temperatures are what they are, but I was wondering if you can comment, because obviously you said no ESR, I understand, but why not optical measurements?
Use some kind of, so I mean,
can you think that it might work?
Yeah, so it depends on what so optical measurements would be very high magnetic fields. That would be, so you could apply people have tried to do the measurements in microwave frequency ranges, so traditional X-band ESR, so those are photons in some sense, right? You apply a magnetic field and you look for microwave absorption. That has not worked. So one can imagine going to much higher magnetic fields for optical emissions, but I don't know that anyone's even tried that. That's outside of it. And I haven't thought much. People do optical measurements at these temperatures. imagine doing that. I don't.
It's not a temperature issue, a heating issue then.
No, I don't think so. Ultimately, I have to think about that. I don't have a good answer to your question as to why that hasn't been tried, but optically detected ESR is not something that I know very much about. But I mean,
You can't do any curve because you don't have the speed for reflecting, right?
right. But yeah, temperature is not ultimately the issue. Because people do optics of superfluid helium 3 at 1 milliton. Those have been done. So that can be done. I mean, that's a hard experiment, but it's not, you know, at Dilfridge temperatures, I don't see any reason why it can't be attended.
The electron bubbles, as you called them.
The ones underneath the surface.
No, the ones in the gallium-arsenide.
Oh, okay, the bubble phase. Yeah, too many bubbles.
The scintillating. So
yeah.
So it seems like you're at a pretty low energy. Are these bubbles? Is this lattice commensurate with the underlying gallium-arsenide lattice?
Yeah, that's a good question. Probably not. It's a
Really?
length scale. I didn't tell you about the length scale, but the length scale for the spacing between the bubbles is at the tip magnetic fields we work at is on the order of 50 to 100 nanometers. So it's much longer length scale than the atomic spacing.
Okay, so I guess, could you elaborate a little on the interactions that cause, you said a couple to a few electrons per bubble, and then some large length scale determining the spacing? That seems interesting.
Yeah, so the reason that happens, it's ultimately governed by the magnetic length and what the length of what's the size of the
Oh, I'm sorry, okay,
yeah.
That makes sense.
And so, okay.
Yeah.
Is that total? That's
well, keep going if there's more to it, but that certainly helps.
And in that region, if you look at the single electron wave functions, for the actual single electron wave functions, they have a lot of nodes in it. It's n equals 2, so it's like, it has 2 nodes in it. And so those nodes allow for the electrons, the individual electrons, to get a little bit closer to one another than they would normally like to be because of short-range Coulomb. They can just get a little, they can kind of overlap their nodes. And in 2 dimensions, the exchange interaction is attractive. So that also wants to pull the system in closer together. But on really long length scales, like sample size length scales, everything has to be charge neutral, right? Otherwise it would collapse. And so it strikes a balance between these competing effects. And depending on what the magnetic field is and the density, it breaks up on some length scale. It's a competition of those things.
Thank you.
Yeah.
Thanks.
More questions?
Lastly, now if 2-dimensional electrons is electron gas, so the electron should move on a plane like a free particle.
Yeah, and they do at low magnetic fields.
What if without any magnetic field? Do they just move around?
They do, yeah. It's an electronic fluid in 2 dimensions, just like a gas, or that's the way that you think about it. That's right.
But can you then detect the gas to liquid transition?
Oh, you're so yeah, it's. I use those 2 terms interchangeably, gas and liquid, in that sense. There isn't really it's a 2-dimensional fluid-like substance of electrons. That's the way I would describe it. It's not there's no transition between a gas and a liquid. There may be actual, like, theoretical theorems and things that say you can't have that transition in 2 dimensions. Shoot.
So I'm just trying to understand in what way your gallium-arsenide today experiment is different from the standard geometry of the fractional quantum Hall effect experiment, for example. Is it that you're putting your context, because what you're measuring is essentially what they call RXX.
Yes, I am measuring RXX.
Magnetoconductivity portion of the experiment.
Yep.
So your contacts, I mean, I'm not very familiar with those experiments, but you had a picture of the currents, right, going around on the edges. So the difference is here that in the whole experiment you have contacts going across the entire sample,
yes,
not just on the edges, or?
Yeah, so what I'm measuring is what you call RXX. It's the longitudinal resistance where, let me go to the other one, sorry. I have a better picture. I know which one you want. I think. This one.
Yeah, so here,
Yeah.
right, so it almost seems like the contacts are only on the edges, right?
Yeah, here they are. They're sampling what happens at the edge.
So in the standard Hall effect, don't they run all across the sample, or?
Yeah, let me go to my backup slide, because I
Yeah,
have
I
a
guess
backup.
I'm trying to appreciate this better. And the structure of the,
Yeah, so
Yeah.
the measurements that we're making, I'm calling V, but those are VXX, or the corresponding resistance is RXX, the longitudinal resistance. Or one can measure, when you push the current through, you can measure the Hall, which is the voltage that's transverse to the current. And in low magnetic fields, if you measure that Hall voltage, then you should measure something that's linear. Essentially, the electrons are just...
so the two contacts, the green wires,
Yeah.
right? Do they go to some metal contacts that run all across the sample
I
surface?
see.
or
Sorry, I
just
misunderstood your question. Yeah, so it's we used it, so we put, you can make the contacts in a number of ways. One way to think about it is just you put metal blobs onto the edge of the sample, and then you heat the sample up, and those diffuse through the crystal lattice, and that's how they make contact with the two-dimensional gas. And so they're shorted out by whatever physics is happening in the two-dimensional gas, but it's not, there's a localized metallic diffused contact here and one here. And similarly for the Hall, there's one out here and one there. Is that?
Yeah.
This is actually in the, I glossed over the fab, but if you want to talk more, but there's maybe.
Yeah, we can talk offline, you don't have to
Yeah.
do it before that. Thank you.
I have one quick question.
Shoot.
So in the isotropic aerogel in the phase diagram, you show only V.
Yeah, I knew. No, you're the first one to ask this question. It's a planted question.
But the susceptibility shows
Both.
yes.
Yeah. So this is that magnetic field issue. So we actually apply a finite magnetic field in our experiments, and that's what leads to a window of stability of the A phase. But we can do the measurements with decreasing magnetic field and trace out where that points. And it points to TC. It points to, it shows that if you could do an NMR experiment in zero magnetic field, you would have only B phase.
All right, let's thank Johannes again for